Now that 8 inches per mile squared. You'd often get examples like, if you're standing on a beach in Florida or driving past the farms of Nebraska, both places where it's relatively flat, the farthest part of the horizon that you can see is about 3 miles away. Now, in my video debunking flat earthers' claim regarding aircraft and level flight, I talked about this equation in great details, including the origin. A quick summary is, this equation is in context of civil engineering, and the error margin gets higher as the distance gets higher. But for short distance, that error margin is acceptable at certain cases. And for a specific distance, this value can even be correct depending where you are. Now let's understand why that 8 inches per mile is wrong and why it matters. There is easy way and hard way. Let's do it the hard way first, based on first principle. After going through the variables, I will propose a test to verify it ourselves. Given a circle with a radius of r and center at 0, 0, your position P1 is top of the circle, and we're interested in position P2, that is d distance away from you. To keep our math simple, let's establish that P1 is always on top. Well, it's a circle, so there is no real top. For our formula, we can rotate the circle to ensure P1's y coordinate is the maximum y value, i.e. on top or very north. I hope that makes sense. We will draw a triangle using P1, P2 and center. This is our main triangle. Then we draw a line from P2 perpendicular to the opposite leg. This gives us two right-angled triangle. Let's call the one closer to circle T1 and the one farther away is T2. The point P3, where this perpendicular line intersects, well, the distance between P1 and P3, indicated by h, is what flat earthers call a drop. Normally we would use Pythagoras to calculate this distance between points. But as we ensure P1 is always on top, meaning its x-coordinate is always 0, thus in our case, this distance is the difference between y-axis. So given a drop, we know y position for P2, which is radius minus drop. Now, if we can get a x position as well, then we can use those positions to create a diagram that would indicate what kind of shape this formula is based on. Note, the distance between these points is not the same as our curvature distance. We can calculate that x position given an angle, lowercase a in diagram, and radius where x equals cx plus r times sine value of a. Our center circle is at 0, 0, thus x simply becomes radius times sine wave of angle. Our origin P1 is also at x0, so we don't need to take that into consideration. As we are testing the y value from our drop equation, we are only interested in x value from a circle. And what is the angle value? Well, the circumference c in whatever unit of our circle spans 360 degrees. So one unit would span 360 divided by c. Given distance d again in the same unit means our angle would be 360 times d divided by c. I will soon be using a spreadsheet, and that requires angle to be in radian rather than in degrees. So in radian value, a equals 360 times d times pi divided by the value of 180 times c. As our circumference c is 2 times pi radius, we can rewrite and simplify the equation till it becomes angle equals distance divided by radius. Plug in the angle value for our P2x calculation, we get x equals radius times sine value of distance divided by radius. And we have our y value from calculated drop using 8 inches per mile square. Before we start plotting this result, why don't we come up with our own equation to compare it with? For our image, we need to calculate the value of drop or h, and that length is radius r minus length of b in triangle T1. Given the angle A in right angle T1, that B leg is called adjacent leg. The hypotenuse is radius. For a right angle triangle, adjacent leg is cosine of angle times hypotenuse. So we start by saying drop h equals radius r minus adjacent side b, which is radius r minus cosine value of angle A times radius r. Making it pretty, h equals r minus r times cosine value of angle. Finally, putting the angle value, h equals radius minus radius times cosine value of distance divided by radius. So that is our equation. For data range, well, imagine you are at P1. Now, if you travel 1/4 of the circumference towards screen right, well, as you're approaching the full distance, your x would approach the value of radius and y would be approaching 0. If you travel towards screen left, your x would approach negative value of radius. So we will use a data range of negative radius to positive radius in miles with 1 mile increment. Please keep this in mind. If our x value calculation is correct, then we should see this being negative radius when distance is lowest. When distance is 0, this value should also be 0. When distance is highest, it should be radius value. Full disclosure here, I don't know how to use a spreadsheet and have no inclination to learn. I just know enough to put these values in and create a chart. I can tell you what shapes the chart would show, but where is the fun in that? What shapes do you think we will get? I'm using LibreOffice Calc, which is a free open source software, but you can use any spreadsheet if you want to follow along. One thing to keep in mind though, as we are using Radian, you need to ensure your calculator spreadsheet is also doing the same thing. Otherwise, you will end up with wrong result. A simple way to check is to get the cosine value of 60. If you get a value of 0.5, then it is calculating in degree. Change it first. To keep our sanity, we will convert all values into a unit like meters. I'll put all the variables used in column A. I'm neat that way. Mile to meter is 1609.34. Inch to meter is 0.0254. Circumference in miles is 24,901. 1/4 of that is integer of cell value A2 divided by 4. Note that we're using integer value for our quarter and lost some precision. Thus, it is only fair that we calculate our radius based on this lost precision. Radius based on c divided by 4 in meter is, after simplifying, is cell value A2 times cell value A11 times 2 divided by pi. Then distance in miles. This is our range column. So first value is negative of cell value A11. Next row is cell C2 minus 1. Copy that cell formula and paste it all the way to row 12,452. Next is the same distance but in meters. So cell value is simply cell C2 times cell value of A2. That is miles to meter. Next column is drop in meter using 8 inches per mile square. So it is 8 times cell C2 times cell C2 times cell value of A5, which is our inches to meter value. Then our drop using our formula in meter. It is cell value A14 minus bracket cell value A14 times cosine value of cell D2 divided by cell value A14 bracket close. Then x-axis value in meter. This is cell value A14 times sine value of cell D2 divided by cell value A14. Next, 8 inches formula drop in Y value. So this is radius minus drop value, cell value A14 minus cell E2. And yes, we immediately notice a negative value. This is the error margin of 8 inches formula. On a perfect circle, drop on a quarter cannot exceed the radius value. Final column, our calculated drop Y value. Again, it is radius minus our drop value. So cell value A14 minus cell F2. All done. Now we can copy these 6 columns and paste the value all the way down to the final row. To validate our x value, with lowest value of distance, it should be a negative radius. Check. At 0 distance, it should be 0. Check. At highest distance, it should be radius. Check. So that looks correct. Next is simply plotting the data using the last 3 columns. We want xy scatter, and usually first column is used as x, which means we would have distance on x-axis and drops on y-axis. Voila! Right? Nope. This is a biased chart. I have mentioned this on one of my other videos, but for the life of me, I can't remember which. Anyway, I discussed how we can manipulate chart to fit a particular narrative. Well, what is wrong with this chart? Well, on default settings, it's compressing x-axis and thus misrepresenting the data. Look at x-axis and the length between 0 and 5 million. Now look at the length in y-axis. In y-axis, it's more than double the length of x-axis. Similarly, if this chart was compressed on y-axis, it would appear flatter. Again, I do not know spreadsheet well enough, so there might be a shortcut. Anyway, to get a correct chart, both axis scale should be the same. So the range for both axes must be same. We should use the highest value for this, which in this data set is the drop value calculated using 8 inches formula, or the very first line of data row value. So we edit the chart to ensure both x and y axis is ranged between negative and positive of that value. Still not done, as I can still change the width or height of the chart to make it appear flatter. So let's ensure the chart has the same height and width. Much better, but I still don't trust it. Well, I will export this as an image and open it in Affinity Photo. Then I can check it a bit better. Once opened as an image, I will use the center and draw a square box. If the axis has the same ratio, the box should touch the same tick value on both axes. If that looks okay, we can move to the next part. Again, using the center, let's draw a perfect circle. Do we see the issue here? Our equation fits the circle like a glove, where 8 inches per mile squared isn't quite right. Wait, it gets worse. Look at this picture of a rubber band, rested, and a circle shape. Now if I would make this circle taller, and it is still rested, well, it is still the same rubber band and has the same length, it just got squished horizontally. And depending on the shape, we would get a different drop value from our arc length. How about when we squish it horizontally? Now it looks wider. Well, that is how our Earth is. It is not a circle but spherical, where it is wider at equator than polar radius. Well, technically according to Neil deGrasse Tyson, it is more like a pear shape. That 8 inch per mile squared matches more the circle that is squished horizontally, while in Earth case is the vertical that is squished. How about easy way? Well, we can fire up Windows 10 calculator app in graphing mode. Then in expression we type in y equals x times 8 divided by 63,360. Because our x is in miles and the result was in inches, we need to divide it further to have y also as miles. And this is the shape. is the same shape we have, but at a much higher range. Instead of stopping at a quarter, if we had continued with our data range, we would be approaching this shape as well. Thus, depending where you are, that equation will have a much higher error margin. Even our equation is not entirely correct, as we are assuming a perfect circle and not a pear shape. Why do flat earthers still use this 8 inches formula? Well, the cynic in me says it allows them to find landmark that according to that formula should not be seen, but is seen in real life. Most often, using a more accurate formula would immediately debunk it. Well, that's all for this video. If you have managed to watch it so far, thank you so very much. I hope you enjoyed it and would give the video a like and maybe a comment to feed YouTube algorithm. If you could also subscribe for similar contents, that would definitely help my small channel grow and would be thoroughly appreciated. Have a safe day. Signing off.